Now that we know what a Taylor polynomial is, let's have a look at how it can be applied. First, let's consider an example similar to the one we already considered in the introduction to this week. Namely, suppose we would like to know the square root of 102. Since 102 is not a perfect square, we want to approximate this value, and we may make use of Taylor polynomials. To do this, we will need to determine two things. Firstly, we need to determine the function of which we consider the Taylor polynomials. And secondly, we will need to determine the point about which we consider the Taylor polynomials. The function is usually rather straightforward. For instance, in the case of square root of 102, we may clearly use the function f of x equals square root of x. Then we may approximate the value of f at x equals 102 to obtain the approximation of square root of 102. Note that we could also use other functions, like g of x equals square root of x plus 100, in which case we would approximate the value of g at x equals 2 to obtain the approximation of square root of 102. For certain practical purposes, it may sometimes be preferable to use a certain function over another, but in general, this is a rather unimportant matter. The main thing is to keep things as simple as possible. To determine the value about which we want to take the Taylor polynomials, we need to keep two things in mind. Firstly, it needs to be a point at which we know the function value, and we know the value of sufficiently many derivatives of the function. Secondly, we need the point to be close to the point where we approximate. For instance, in the case of f of x equals square root of x, to approximate square root of 102, we need to take Taylor polynomials around a square, since then we will know the function value, and the value of all the derivatives as fractions. Thus we consider 1, 4, 9, 16, 25, 36, and so on. And we see that 100 is the closest square. So, we consider Taylor polynomials about x equals 100. So, let's consider the obtained approximations. The 0th order Taylor polynomial is simply the function value at the point x equals 100. So our first approximation is that the square root of 102 is approximately square root of 100, which is 10. The 1st order Taylor polynomial is the linearization at the point x equals 100. So to approximate the function value at x equals 102, we evaluate the linearization at x equals to 102 to obtain the approximation 10 plus 1 over 20 times 102 minus 100, which is 10.1. Here the 1 over 20 comes from the fact that the derivative of the square root is 1 over 2 times the square root. Note that the first term remains the same, so we get 10 plus a new term. The 2nd order Taylor polynomial is obtained from the 1st order Taylor polynomial by adding the term 1/2 times the second derivative of f at the point a times x minus a squared, where in this case a equals 100 and x equals 102. Since the second derivative of the square root equals minus 1 over 4 times x times the square root of x, we obtain for the 2nd order Taylor approximation the value 10.1 minus 1 over 2000, which is 10.0995. By adding the terms for the 3rd and 4th Taylor polynomials, we obtain the following further approximations. In practice, we determine which Taylor polynomial is needed by considering the precision needed for the context. For completeness, we have compared the obtained approximations to the result from a calculator. Note that the approximation error decreases as the order of the Taylor polynomial increases. How quickly it decreases depends on the particular function and the value at which we approximate, which is why we should choose those carefully, as mentioned earlier. Let's consider another example. Namely, let's see if we may approximate the value of Euler's number e. Again, we will need to determine a function and value about which we take the Taylor polynomials of that function. For a function, the most obvious thing to consider is f of x equals e to the power x. Note that we should not assume to know the value of e, since that is what we are trying to approximate. Luckily, we know the value of f at least one point, namely x equal to 0, since e to the power 0 equals 1. Now, since any derivative of e to the power x still equals e to the power x, we will also know the value of any derivative of f at the point x equals 0. So we may use Taylor polynomials of the function f of x equals e to the power x about the point x equal to 0 to approximate f of 1, which equals e to the power 1, which is just Euler's number e. Here we see the first couple of approximations so obtained. Note again that each time we go up 1 degree, we simply add a new term to the previous approximation. Again, if we compare the obtained approximations to the output of a calculator, we see the following approximation errors. Note in particular that the approximation errors are a lot higher at the same order when compared to the approximation errors of the square root of 102. In particular, we will need higher order approximations to get the same precision for Euler's number compared to the square root of 102 when using this method. Now that we have considered Taylor polynomials both in definition and in application, let's do some exercises to practice.